Hello, my name is Werner Seibold and this is my argumentative exposition. For the development of our automated system, we employed a combination of design methodologies and strategies to ensure an effective and user-friendly solution. Our primary design methodology was the user-centered design (UCD) approach. This involved conducting thorough research and analysis to understand users' needs, goals, and behaviors. We identified pain points, efficiencies, and areas for improvement in the existing process. Based on this analysis, we generated design concepts and used techniques like wireframing, storyboarding, and prototyping to visualize the interface. Our goal was to create a simple HMI structure where users can access their desired outputs with just 2 clicks. This user-centric approach ensured that the system's design aligned closely with users' expectations and requirements. In addition to the UCD, we also implemented a mold-based design, MBD methodology. MBD enabled us to develop dynamic and multi-domain molds of the mechatronic system using specialized tools and simulation environments. We designed and optimized control algorithms based on these molds using techniques such as state machines, block diagrams, structured text, and algorithmic models. We validated the control algorithms and system behavior through hardware-in-the-loop, HIL simulation, where we connected the virtual molds to physical hardware components in real time. This iterative process allowed us to fine-tune the design and optimize the performance of the automated system. To ensure a seamless user experience and efficient operation, we incorporated various design strategies. Firstly, we focused on clear, consistent layout across different screens and elements with the interface. The standardization helped us users navigate the system easily and locate desired functions quickly. We also empathized information hierarchy by organizing information in a logical and hierarchical manner. Important and frequently used functions were prominently displayed, while less critical information was presented in a visual, distinct manner. This approach enabled users to prioritize and access essential information efficiently and faster. Visibility and feedback played a crucial role in our design. We provided clear visual feedback to inform users about system responses to their inputs. We used visual cues such as animation, color changes, and progress indicators to indicate ongoing processes and completed actions. Additionally, we assured that the interface displayed clear and readable text and graphics, enhancing overall user comprehension. Furthermore, we employed a modular approach to divide the complex process into smaller, manageable modules or steps. Each model was automated individually with clear inputs, outputs, and interfaces between them and connections. This modular design facilitated easier development, testing, and troubleshooting of the system. Lastly, we aimed to minimize cognitive load for the users. We simplified the interface by reducing unnecessary elements and avoiding clutter. We presented information in a clear and concise manner, utilizing progressive disclosure techniques to reveal information gradually based on the user's context and needs. By integrating these design methodologies and strategies, we developed an automated system that prioritizes users' needs, ensures efficient operation, and provides a seamless user experience. The automated proposal that we made over the course of the semester with the usage of the 3 stations and the implementation of codices and Schneider, and also the connection between the stations and programs, that they connect with each other, involves a lot of control, where each of the line of code has to be verified by sensors. And for example, no piece in the station 1 will be moved onto the conveyor if the conveyor is moving, or another example, that the cylinder won't extend if there's a piece in the final sensor waiting to be processed. The system we developed also has the highest quality. So we implemented sensors that check if the piece is always correct and that there can be no mix-up between pieces, either metallic or plastic. In addition, the system has a high repeatability, which means that the pieces will always come out the same way. The productivity in the system can be better because sometimes it works a little bit slower because of the condition that needs to be concluded before it can proceed. But in overall, the productivity of our system is high, with a good quality of the pieces. The safety aspect of our system was very important to us and therefore is high as well, where we did not only implemented the emergency button in each station, which is a physical button, but also in our HMI. that stops the whole process directly. This is very useful, for example, when maintenance needs to be done in all stations or just one in particular. As well, when the system acts if good pieces are delivered. Otherwise, it will throw out the piece and not use it furthermore. The implementation of our system was fairly good. We had no problems connecting the stations to each other and sending the information between each PLC. The problems occurred when we implemented codices in our system. As first, we couldn't connect the virtual PLCs to our actual PLCs, which caused problems that we couldn't read the signals we need for our counters and timers. After a lot of questioning and reading, we figured out on how to receive the data and how to connect it properly and started receiving data from Schneider. Once we could send and receive data, we adjusted our memories that they sent the information so it's more accurate. After all the timers and counters, plus the lights and the switches were configured correctly, we ran the program to see if everything works properly and there were no mistakes or errors in the system. The technologies that we used for the implementation of our system were Schneider Electric and codices. Both of them are software to program PLCs. Those two programs are perfect for the programming of PLCs. First of all, we're using Schneider M221 PLCs. Therefore, the Schneider program is made for those PLCs. Codices can also communicate with these Schneider PLCs, but it's not ideal. Therefore, the combination of both programs gives us the best results in our animation and automation. The software tools that we used in our Schneider were timers on timers and timers off timers, as well as counters and operation and comparison blocks. The operation blocks were used to save values in the memory words that we used. The comparison blocks were used to compare either the memory words to a certain value or the encoders of the arms to a certain value. Furthermore, we used high-speed counters to have our encoder values of each of the arms that we used. In codices, we used on and off timers as well as counters to count if the pieces that each station has. We also used the structured text for if clauses and to store values of our memory words in Schneider and codices. We also used the move function to store the ET value of a timer to a certain variable. We also used the equal function block to compare counters to the piece that it is right now. In addition to that, we used the visualization block to create a HMI where our values, lights are shown. Also in the HMI, we have our buttons that control the system. We also use the Ethernet functions to connect our codices program to the Schneider program. The Ethernet function was more on the outside, and in this Ethernet function we assigned the variables that we are using and how they are called in our progressive program. Thank you very much.